For motion and forces, otherwise known as dynamics, let's start with investigating kinematics. Kinematics, the branch of classical mechanics that describes motion without regard to forces and other physical processes. Easily applicable in our lives, everything regarding motion has something to do with this topic. For example, when I go to school, I grab my stuff and get to the wheel. As I drive, my motion can be described through the use of kinematics. Pulling away from my driveway, I accelerate from rest. Coming to a stop sign or traffic light, I accelerate to a halt. My velocity? I can either look at my speedometer, which measures my speed relative to the ground, or take a look at my surroundings and measure my velocity relative to the things I see. Maybe that pedestrian. Maybe that vehicle on the other side of the road. Maybe that car right in front of me. For a display of displacement and distance, simple calculations using the formulas learned in class do the trick. Even projectile motion can be exhibited through driving, although I should note rarely. Like the questions found in textbooks and worksheets, if a car happened to drive off a cliff, projectile motion would be relevant. The possibilities are truly endless with driving and kinematics. Beyond this idea, kinematics has found its way into the technology we rely on nowadays, even for driving. How so? Well, say I forgot the route to school. What would I do? Number 1, I would open maps. Start from my house, destination, to school. But how does maps know my estimated time of arrival? And how does it know which route is best to take? This may be surprising, but the GPS's functionality is based on kinematics. Now, let's dive into the brain of the GPS just to understand it a little bit better. A GPS system is made up of 3 components: the satellite, the ground station, and the receiver. These parts send signals to one another, and in the case of maps, my phone acts as a handheld receiver, which figures out my position in the world by communicating with the satellites in space and the ground stations here on Earth. As I ask for directions from my home to my school, these 3 parts communicate with one another to find the shortest path of travel, which becomes my distance. Following this, knowing the speed limits of the roads on the designated path, the GPS system will calculate my ETA, my estimated time of arrival, which is deduced from the estimated time of travel. While driving, the GPS continues this communication back and forth, and relative to the stops I take and the traffic I encounter, the estimated time of arrival and route will update accordingly. Unsurprisingly, all these calculations are made using the kinematic formulas learned in class. Cool, right? Even autonomous vehicles utilize the fundamentals of kinematics in its workings. For example, when switching lanes, the car must check that there's sufficient distance between it and the other vehicles on the road before completing the maneuver. Essentially, its integrated computer performs the familiar 2-second rule for driving and utilizes our well-known kinematics formulas to base conclusions. Thanks to the safe environment harbored by autonomous vehicles, the need for safety equipment such as strong glass and airbags will drop in vehicle production. With this, not only is a world with just self-driving cars safer, but the vehicles themselves will be much lighter than the traditional ones. That means that they'll use less fuel and energy, thus causing less harmful emissions. Kinematics and technology, a power couple. The 2 combined have and will continue to pave the way for technologies around the world. Having mentioned the role of kinematics in driving, why not segue this idea over to forces, starting with one of the most important scientific breakthroughs that unlocked the age of technology: Newton's 3 laws of motion. Before Papa Newton, as my physics teacher refers to him as, our understanding of how objects moved in the universe came from the ancient Greeks. Why do objects fall to Earth? According to Aristotle, it's because objects longed to be united with the ground. And why would these objects slow down when we put them in motion? Because they get tired. Duh. Well, we know it doesn't work like that from Papa Newton. Now, with an understanding of his infinitely more advanced laws of motion, the motion of pretty much everything can be explained. As I drive, I push down on the gas pedal and the car starts to move forwards. I push harder and pick up speed. At some point, I ease off the gas pedal and keep the car moving at a constant speed down a straight stretch of road. And when I want to slow down, I lift my foot off the gas pedal before pressing on the brakes. Though a complicated series of events, Newton's second law is powerful enough to explain each component. Of course, not the inner workings of the car necessarily, but the relationships between the amount you step on the gas pedal and the car's changing speed. From the formula, F equals ma, it can be deduced that the amount of force varies directly with the amount of acceleration. Specifically with me and the car, which makes up a system, the more force I apply to the gas pedal, the greater the acceleration of the system, me and the car, and vice versa. So now, doesn't Newton's first law state that an object in motion will remain in motion? Why does my vehicle not maintain constant speed when I take my foot off the gas pedal? Well, it should be pointed out that there's a net external, unbalanced force acting on the car: friction. If I were to draw an FBD of my car on a flat road, along with the normal and gravitational force, a frictional force exists. This frictional force ultimately affects the motion of the vehicle and will cause it to slow down. Lastly, the third law. This law states that action and reaction are equal and opposite. In short, for every action, there will be an equal and opposite force causing a reaction. While driving, the wheels exert a force into the ground, and the ground exerts a force equal in magnitude but opposite in direction, creating the action-reaction pair. Same for walking. When you put your foot on the ground, you are applying a force to it. In doing this, the ground actually applies an equal force onto your foot, in the opposite direction, of course, pushing you forward. It's as simple as that. Now, taking all these ideas from dynamics, what technologies out there have taken into consideration and applied these mentioned concepts? For one, look no further than the seatbelt. Seatbelts have been designed for human safety, and considering Newton's laws, if a passenger were to not wear a seatbelt, they would not stop simultaneous to their vehicle due to their inertia, causing them to continue moving in the same direction until an equal and opposite force acts upon them. Now, considering the acceleration of the car, the net force which is exerted on an individual could potentially be fatal. For a driver, the effect of the three laws usually amounts to slamming into the steering wheel or dashboard or hitting the windshield, whatever comes first. The invention of the three-point seatbelt provides a means by which the stopping of a vehicle would lead to a stopping of the rider. And although seatbelts have been around for decades and have saved a whopping number of lives, there are still vast improvements that can be implemented. I propose the innovation of an automatic, smart, customized seatbelt. This seatbelt would automatically sense one's height and weight, for example, and tailor the belt according to those specifications. There could be seatbelts for kids, seatbelts that account for one's posture, seatbelts in short that account for the diversity of people who rely on them daily to keep them safe. By factoring in those specs, the smart seatbelt will adjust to the rider and limit potential injuries. In this way, this new and improved seatbelt accomplishes the task of keeping riders safe even better than the widely used three-point ones. The final subtopic covered in dynamics was uniform circular motion. For a brief overview, we learned that an object in uniform circular motion experiences a centripetal force pointed towards the center of the circular path the object takes, meaning its acceleration also points towards the center. We also learned that the velocity of an object is tangent to the path it takes, which is 90 degrees to the acceleration. Following this idea, we learned that the centripetal force applied must be sufficient, or else the object itself will leave the circular motion by following the tangential speed it was traveling at prior to the insufficient force. One last idea covered was that with circular motion, there is a fictitious force known as the centrifugal force, which is associated with it due to the object being in a rotating frame of reference. Taking these ideas into account, we can continue to relate to driving. A concept that continually arose in our learning of circular motion was the idea of banking roads, an engineering feat which has secretly aided drivers, especially in tough weather conditions. When a car drives around a bend, there exists a net centripetal force towards the center of its circular path. If the road is flat, that force is supplied by friction. However, what happens if the frictional force is insufficient, such as during black ice? Well, to say the least, the car would end up in an unwanted situation. In order to ensure that cars don't skid off the road, engineers have come up with banking curves. When a curve is banked, the centripetal force can be supplied by the horizontal component of the normal force. In fact, for every banked curve, there is one speed at which the entire centripetal force is supplied by the horizontal component of the normal force, and no friction would be required. Though banking curves is great, is there a way to make driving around bends even safer? Of course. Some locations have started painting jagged or sharp lines on bending roads to frighten drivers to slow down. Essentially, the lines act as an illusion where the lines give a speeding perception, alarming drivers. Statistically, this tactic has reportedly decreased crash and skid rates by 36%, and I believe this is one of the best psychological tricks to reduce speeding and improving safety. Overall, even if there are still many risks that come with driving, due to the invention of banking and the application of physics, driving has become exponentially safer. To summarize all that's been said in this video, the principles and concepts from dynamics are applicable in several ways just in our day-to-day life. All we have to do is look at our world through a different lens to truly uncover the physics hidden in plain sight.